Hello dear students, welcome to the third lecture on heat exchangers. Uh, Unlike I've said in the last lecture, uh, I think it is better to continue with the lecture before actually solving the problems because we need to have some more theoretical concepts to be gained before actually solving any problems. So I thought of giving the concept of effectiveness, NTU, derivation of effectiveness NTU relations, etc. First in this lecture, and then in the next lecture onwards, we will be solving problems both from the LMTD analysis type as well as in the effectiveness NTU method. So before deriving the effectiveness NTU relations, we should know what is meant by effectiveness and what is meant by NTU. So let me first discuss about the temperature variation of hot and cold fluids, especially in the case of a counterflow heat exchanger. So let's see that. Here this figure, schematic diagram, there are two figures of these. Both are counterflow heat exchangers. The temperature variation of hot fluid and cold fluid in counterflow heat exchangers. So let's see the difference between these two. Now we know that the heat transfer is given by Q is equal to m dotted CH into THI minus THO. That can be written as CH, capital CH THI minus THO, which is also same as CC into TCO minus TCI. Again, a third equation is there which will give you the relation connecting the heat transfer, the overall heat transfer coefficient, the area, and the average temperature difference. We call that LMTD. Now, heat transfer is equal to CH into THI minus THO, which is also equal to CC into TCO minus TCI. Now we have two fluids having mass flow rate m dot h and specific heat CH, and another one mass flow rate m dot c and specific heat CC. So now while taking this product MHCH, we call it capital CH. This is the heat capacity rate of the hot fluid, and this is CC, heat capacity rate of the cold fluid. So CH into THI minus THO should be equal to CC into TCO minus TCI. Now compare the values of the heat capacity CH and CC. Now since the product of these two terms should be equal, now we can have different cases. The heat capacity rate of the hot fluid is more than that of heat capacity rate of cold fluid. I repeat, heat capacity rate of hot fluid is more than the heat capacity rate of cold fluid. So in that case, in order to satisfy the product to be equal, if heat CH is more than CC, then we can say that if CH is more, then THI minus THO should be less than that of TCO minus TCI. If this is more and the product to be equal, then this should be lesser among these. That is, a fluid with a higher value of heat capacity rate will have small temperature variation. So let's see the figure here. Now in this case we know that CC, heat capacity rate of cold fluid, is less than that of heat capacity rate of hot fluid. So in that case the hot fluid will have lower temperature variation as compared to hot fluid. The hot fluid will be having more temperature variation. On the other hand, we take the same case of a counterflow heat exchanger where the heat capacity rate of hot fluid is less than that of heat capacity rate of cold fluid. In this case, we can see that the one which is having lesser value of heat capacity will undergo more temperature variation in order to satisfy the equation. So here the hot fluid will undergo more temperature variation as compared to cold fluid, as can be seen from this diagram. Now another fact with regard to a heat exchanger is that let's assume that the mass flow rate of the hot fluid as well as cold fluid, they are fixed actually. So in any heat exchanger, mass flow rate will be fixed. The hot fluid also the temperature of hot and cold fluid, inlet temperatures of hot and cold fluids are also fixed. Why? Because under steady state conditions the mass flow rate should be the same, and also the inlet temperature of hot fluid and cold fluid should be the same. Now what about the outlet temperatures? The outlet temperatures, uh, basically these are the things which are known to us. The parameters known to us are inlet temperature of hot fluid as well as inlet temperature of cold fluid, and also the mass flow rate also known. These two temperatures are actually established in a heat exchanger based on the overall heat transfer coefficient, area, and parameters like that. So this is fixed and this is fixed, and uh, based on whether Cc and Ch, based on the relative values of heat capacity rates of hot and cold fluids, these outlet temperatures will be fixed. Okay, now we can think another case. What is the maximum heat transfer possible? Okay, maybe why are we interested in the maximum heat transfer possible in a heat exchanger? That we'll see later. So let me go to the definition of effectiveness of a heat exchanger. Now the effectiveness of a heat exchanger is defined as the ratio of the actual heat exchange to the maximum possible heat exchange. Here it should be 2 to the maximum possible heat exchange. So it is usually represented by Greek epsilon. Epsilon is equal to actual heat transfer rate divided by maximum possible heat transfer rate. In a heat exchanger, the actual heat transfer rate can be calculated by any of the three equations given here. So Q is equal to mh mhch into thi minus tho, that is capital Ch into thi minus tho. If we know mass flow rate, specific heat, inlet and outlet temperatures of hot fluid, we can calculate this. Similarly, from this equation also we can calculate the actual heat transfer rate, and also if all the parameters here are known, we can also calculate heat transfer rate using the convection equation. Now, what is maximum possible heat transfer rate? In the case of a heat exchanger, the maximum possible heat transfer rate could be or can be calculated like this. Like now consider the case heat capacity rate of cold fluid is less than heat capacity rate of hot fluid. Now we do one thing. We have a particular heat exchanger which has uh, a particular area or length, a fixed length, maybe 2 meter or 1.5 meter, like that. Now what will happen if we increase the area of the heat exchanger or increase the length of the heat exchanger? So the fluids are supplied at their inlet temperatures T hot in and T cold in. Now if the length is increased, then this hot temperature, this temperature will be corresponding to length of 1.5 meter. If it's increased to 2 meter or 3 meter, what will happen? This temperature THO will decrease further to some other temperature. We should probably elongate this graph such that this THO will be a smaller value, and similarly THI will be introduced here, and the THI will increase further like this. So now what if it is the length is increased to very large value, maybe infinity. Actually, we cannot increase that to infinity, but as a limiting case, what will happen if we increase the length of the heat exchanger or the area of the heat exchanger to infinity? We have a heat exchanger with the infinite area. In that case, uh, this will be decreased further, or THO will be increased further. Now, which one? Which one will have more variation of temperature? The The fluid which is having lower heat capacity will be undergoing higher variation of temperature. I repeat, the fluid which is having lower heat capacity will undergo high temperature variation. That is the difference between inlet and outlet temperatures will be more in the case of a fluid having smaller value of heat capacity. So in this case, Cc is smaller than C hot. That means if you increase the length of the heat exchanger to infinity, eventually what happens is like TCO will be increased to THI. This is the maximum temperature to which TCO can increase as a limiting case. So TCO will tend towards THI. Okay. Now we take the other case. If CH is less than CC, that is hot fluid is the fluid is having lower value of heat capacity. In this case, hot fluid will undergo more temperature variation. Now for this heat exchanger, if we increase the length to infinity, what will happen? THO will be decreased and THO will tend towards TCI. So in the limiting case, there can be two cases, any of the two cases possible. One case is like a THO will, sorry, TCO will tend towards THI, or THO will tend towards TCI. I repeat, either TCO will tend towards THI or THO will tend towards TCI. So any of these cases can happen. Both the cases cannot happen simultaneously. In order to satisfy the energy balance, any of these can happen. So now what will be the maximum possible heat exchange or heat transfer that is given by uh, the limiting case? Like if cold fluid is the fluid with the minimum heat capacity, then the maximum possible heat transfer will be the minimum heat capacity into the maximum temperature difference. What will be the maximum temperature difference? TCO will tend towards THI. So instead of writing TCO minus TCI, we can write THI minus TCI into its high heat capacity. Or if CH is the fluid having minimum heat capacity, this will be heat capacity of the hot fluid, minimum fluid. So CH into THI minus, instead of THO we will write TCI because THO is going to tend towards TCI. So what will be the case? Now we have, I'll go to the next slide. Now we have two cases. Either hot fluid or cold fluid will be the fluid having minimum heat capacity, right? So the fluid having minimum heat capacity rate is called the minimum fluid, and the fluid having the maximum heat capacity rate is called the maximum fluid. So the heat capacity rate of the minimum fluid we call C min, and heat capacity rate of the maximum fluid we write C max. So now the maximum heat transfer will be is given by minimum heat capacity into the maximum possible temperature variation. That will be equal to Thi minus Tci. Whatever be the case, like if it's whether it's the hot fluid is the minimum fluid or cold fluid as the minimum fluid, maximum heat transfer is given by maximum possible heat transfer is given by minimum heat capacity into Thi minus Tci. So now we have epsilon is equal to actual heat transfer rate divided by maximum possible heat transfer rate. So we go to the next slide, we can see that uh, if hot fluid is the minimum fluid, assume that hot fluid is the minimum fluid. Actual heat transfer can be written as Q is equal to CH into Thi minus Tho. That is equal to, we call this C min is equal to CH. So we write this equation as C min into Thi minus Tho. We write this in terms, okay, even the T also is uh, as a subscript. I'll make the change now itself. There are many such errors in my slide. Okay. So heat transfer, if hot fluid is the minimum fluid, C min into Thi minus Tho. This is the actual heat transfer. And what is the maximum possible heat transfer? Maximum possible heat transfer is always given by minimum heat capacity into the maximum possible temperature difference, Thi minus Tci. This is a case where a heat exchanger with the infinite area. So Qmax is equal to Ch into Thi minus Tci. That is equal to, here hot fluid is a minimum fluid, so C min into Thi minus Tci. So actual heat transfer is C min into Thi minus Tho, and maximum heat transfer is C min into Thi minus Tci. So now effectiveness is equal to Ch into Thi minus Tho. Okay. I'm making the changes on the subscript. I did not use the equation editor. Certain things are written the other way, so the subscript are changing back to the normal forms. Okay, now they are converted. Okay, effectiveness is equal to CH into THI minus THO divided by CH into THI minus TCI. So, in this particular case, if hot is the minimum fluid, both will be written as Cmin into this divided by this. So, if you write like this, write the heat transfer in terms of the minimum fluid, then only this will become Cmin by Cmin. Will get cancelled, and it is merely going to be ratio of the temperature differences. Temperature difference of the minimum fluid divided by maximum possible temperature difference. This is going to be like this. Now, on the other hand, if cold fluid is the minimum fluid, again we can get a similar relation. So, Q is equal to Cc into Tco minus Tci, and since cold fluid is the minimum fluid, Cc we will write Cmin into Tco minus Tci, and Qmax is written as Cc into Thi minus Tci, and Cc is the minimum fluid, so Cmin into Thi minus Tci. Then effectiveness will be written as actual heat transfer divided by maximum possible heat transfer. So we write the actual heat transfer in terms of the minimum fluid, in terms of the minimum fluid properties for comfortable only, comfort only. So, sorry, convenience. So this will be Cc will get cancelled, Cmin by Cmin. Cc is the minimum heat capacity, so effectiveness will become Cmin by Cmin. So if you write effectiveness in terms of the minimum fluid, the equation will either be Tco minus Tci divided by Thi minus Tci if this is a cold fluid is a minimum. If hot fluid is a minimum, we can write this in terms of Thi minus Tho divided by Thi minus Tci. So anyhow, effectiveness will be written as a positive quantity. We are interested only in the magnitude of it. So the maximum possible value of effectiveness will be 1. Now another parameter of significance is the parameter called number of transfer units, or NTU. In short, in certain equations, NTU is simply written as N, which is the ratio of conductance to the capacitance. So, UA is the heat conductance. Inverse of the resistance is UA, conductance divided by capacitance. So, conductance of the fluid divided by minimum heat capacitance is known as the number of transfer units of the heat exchanger, NTU. We write this as NTU. This actually represents the size of a heat exchanger. Now, the heat exchanger analysis using LMTD was discussed in the previous lecture. So, we know that heat transfer is equal to overall heat transfer coefficient into total area into LMTD. We can calculate the heat transfer if all these things are known: overall heat transfer coefficient, total area, and this. Or any of the, if heat transfer is known and any of the parameter is missing, we can calculate that particular parameter. For example, the missing parameter is the area of the heat exchanger, or rather length of the heat exchanger. So in that case, we can calculate the length knowing total heat transfer, overall heat transfer coefficient, and the LMTD. LMTD can be calculated using any of these equations for counter flow and parallel flow, or maybe for other heat exchangers we can calculate LMTD, provided we know inlet and outlet temperatures of both the hot and cold fluids. So there are 4 temperatures: inlet temperature and outer temperature of hot and cold fluids, Thi, Tci, and Tho, Tco. Counter flow, parallel flow, or any other type of heat exchanger also, we can calculate the LMTD provided all the 4 temperatures are known. or the outlet temperatures could be can be calculated using MCP delta T relationship. So anyhow, the inlet temperature of hot and cold fluids will be known, and if the mass flow rate of them and the specific heats are known, we can calculate the outlet temperatures of hot and cold fluid from the corresponding relations, like Q is equal to mH CH Thi minus Thi. From these relations, we can calculate any missing temperature like this, provided mass flow rate and specific heats are known. And the heat transfer can be calculated, or any missing parameter can be calculated only if we know delta T, that is LMTD. Now, what will happen if we don't know this value of LMTD? We cannot calculate this value. This can be calculated only if we can calculate the outlet temperatures also. So, in that case, either analysis of the heat exchanger using LMTD method will be an iterative procedure, which is very tedious way of calculating it. So in that case, what we do is we go for another type of analysis of the heat exchanger using relation connecting effectiveness NTU, effectiveness and NTU. We'll see how it is. We go back to this slide. We know that effectiveness is equal to either Thi minus, that is actual heat transfer divided by maximum possible heat transfer. So this is very interesting actually. This is a very wonderful technique to analyze a heat exchanger even though we don't know all the four temperatures. So actual heat transfer divided by maximum possible heat transfer. So and the actual heat transfer is equal to is given by CH into THI minus THO or CC into TCO minus TCI. Maximum possible heat transfer is given by minimum of CH and CC into THI minus TCI. THI minus TCI. Minimum of this into. The fortunate thing is that in all the cases, the temperature at which hot fluid and cold fluid are admitted can be it will be known. So in that case, the maximum heat exchange or heat transfer, maximum possible heat transfer can be calculated if we know C min, minimum of the heat exchanges under this are known. So now knowing a relation like Q by Q max is equal to epsilon. Okay, Q by Q max, actual heat transfer divided by maximum possible heat transfer is equal to epsilon. So if we can somehow calculate epsilon even without knowing the temperatures, all the four temperatures, actual heat transfer can be written as epsilon into maximum possible heat transfer rate. And the maximum possible heat transfer rate is always given by minimum of the heat capacity into Thi minus Tci. Thi and Tci will be known in all the cases. If at all some temperatures will be unknown, they will be Tho and Tco. So maximum possible heat transfer is given by C min into Thi minus Tci. And in addition to this parameter, if we can calculate, obtain epsilon without actually knowing the outlet temperatures, then we can calculate actual heat transfer rate is equal to epsilon into maximum possible heat transfer rate. So this method can be used. So now the task is to establish a relation for epsilon effectiveness, an equation for effectiveness which will not have temperature terms in it. So if we can have a relation which for effectiveness which does not require all the four temperatures, then we can calculate the heat transfer rate and any other missing parameter like the area of the heat exchanger or length of the tubes of heat exchanger and things like that. This is an idea behind derivation of a relation for effectiveness of a heat exchanger.